just think philosophically, think about it. You're Mother Nature, and you've been really successful with green plants, using photosynthesis, exploiting the energy of light. You know, when animals can forage, they can get their energy, their food, from plants. That works, but Mother Nature is scratching her head. So should I just discard it, forget about it, and go for the food? Or should I maybe keep it in reserve? If I were Mother Nature, I would say, well, you know, it's been successful. Why discard it? To build this kind of water from ordinary water, to build fourth phase water, requires energy, of course, and the energy comes from light.
Actually, there's some research coming out that even if we take in chlorophyll, we can actually make energy from that via our mitochondria just by ingesting it and just having the sun hit our skin.
One of the reasons why this weed killer kills weeds is because it diminishes the amount of easy water, and that impairs function in all of the cells of these plants that we refer to as weeds.
Welcome to the Live Damn Well podcast. My name is Jorge Roman, and my guest today is Dr. Gerald Pollack, professor of bioengineering at the University of Washington. Dr. Pollack's research is centered around the most important building block of life, water. As a result of his research, Dr. Pollack authored The Fourth Phase of Water, Beyond Solid, Liquid, and Vapor, shedding light on a critical component of life which simply doesn't get the spotlight too often. He's founding editor-in-chief of the journal Water, executive director of the Institute for Venture Science, 2015 recipient of the Brandlaureate Award, and 2016 winner of the first international Emoto Peace Prize. Dr. Pollack, thank you again for coming on the podcast.
Oh, it's my pleasure, Jorge. Happy to be with you, and thanks for inviting me.
So before we get into exactly what the fourth phase of water really is, I want to introduce an interesting concept that I heard on your TED Talk, which was really, really cool, by the way. So we know that we get our energy from food, but your research also suggests that humans, much like plants, can also get our energy from sunlight. So can you explain that concept a little bit more?
Okay, well, it's an unusual place to start. Before discussing the fourth phase of water, but just think philosophically. Think about it. You're Mother Nature, right? Okay, and you've been really successful with green plants, using photosynthesis, exploiting the energy of light, and even some single-celled organisms will photosynthesize too. And now you've gotten bored and you decide, well, you know, I've done pretty well with single-celled organisms, bacteria, such, and green plants. And I think I'll invent humans or invent animals. You know, when animals can forage, they can get their energy, their food from plants. That works. But, you know, this photosynthesis mechanism based on light has been so successful. What shall I do? You know, Mother Nature is scratching her head. So should I just discard it, forget about it, and go for the food? Or should I maybe keep it in reserve? Keep it in reserve for perhaps supplementation of the food that you would get through foraging, or a reserve of some sort. You know, and being wise and conservative, Mother Nature, if I were Mother Nature, I would say, well, you know, it's been successful. Why discard it? It makes a lot of sense to use it. And so philosophically, it makes total sense that we as humans, and also, of course, other animals, could use the energy from light as a supplementation or backup or what have you. It makes philosophical sense. And so now you say, well, okay, well, philosophical sense is okay, but what about evidence? Is there any evidence that, you know, that we use light? And most of us don't don't really think about that, but I thought about it. And one piece of evidence, or I should say maybe a major piece of evidence, it has to do with this fourth phase of water that you mentioned. So how does light relate to the water, to the fourth phase? Well, the fourth phase is a phase of water that that we uncovered. I hate to use the word discovered because there have been hints of such for 100 years or so. So maybe uncovered is better than discovered. And what we found through our experimental studies at the University of Washington is that to build this kind of water from ordinary water, to build the fourth phase water, requires energy, of course, and the energy comes from light. Now, I said of course, but why of course? And the reason is, if you want to create order out of chaos, you need to put energy in. Fourth phase water is ordered water. The molecules are organized in some way, and it's built out of ordinary water, whose molecules are randomly disposed and bouncing around at a fierce number of times each second, or each femtosecond even. And in order to convert that randomly, those random molecules into ordered molecules, you need to put in energy. And we found the energy comes from light. You know, and many people are not so familiar with this principle of thermodynamics or physical chemistry, but you can glean it from thinking about your office. So your office becomes progressively more messy. You know, the papers are strewn all over, and it doesn't require any energy to do that. You throw this paper here, and this book there, and this pencil there, and this laptop here. And if you want to organize it, you got to put in some time and energy to organize it. And so that illustrates in a familiar way the principle of requiring energy to create order. And that principle applies also in physical chemistry, and also especially to water. So if you want to build this kind of fourth phase water, you need to put in energy, and the energy comes from light. Okay, so if you buy that principle, you say, well, so what? Okay, and the so what is that this water that fills your body, this fourth phase water fills your body, and it's got this energy that it received from the light. It's, you might say, it's potential energy. It's energy that can do work. You see, and some of the work that's done by your body actually does come from this kind of water, and the evidence for that is detailed in the book previous to the one that you mentioned. The fourth phase of water is the more recent one, but cells, gels, and the engines of life, and that book, one of the principal themes of that book is that the work of the cell, every cell in your body, involves the water. It involves this fourth phase of water. At that time, this is almost 20 years ago, we didn't call it fourth phase, but essentially it's the same. It's ordered, structured. We called it, as other people have called it previously, structured water. And that water is centrally involved in the actions, in the work of the cell. So, okay, to summarize, to make a long story short, the ordered water, the fourth phase of water, is critical for everything, for supplying at least some of the energy in your body. And that requires energy to build. And the energy for building comes from light. So, in fact, if you follow the trail of argument, we use light to build energy that's stored in this fourth phase water, and that energy is used to do what your body needs to do. And so therefore, in a sense, or more than just in a sense, we actually do make use of light energy for function. I think, I'm sorry to drag on with that, but it involves a few steps of development in order to understand it. And it leads to, um, um, I'm sorry, I'm ragging on, but there's so many things to say. It leads to, to this concept that some people know about and other people think is just fiction. And that is that some people can actually live mostly without food. And so the question is, and I know some of these people, and there's a lot that you can find. For example, there's a film that's produced by a guy named Straubinger from Austria, and it's called "In the Beginning There Was Light," if I have it correct. And in it, he interviews about 20 different people who don't eat. See, and they do just fine. And I was recently contacted by a woman who's a dancer, a woman from California, and she contacted me to find out about this issue of where she gets her energy and such. She says that, she dances, and dancing requires huge amounts of energy, of course. And sometimes she says, well, she just decides, or she feels like not eating. And so she'll go for 3 or 4 weeks without eating, and then she'll start eating again. And during this time, she's still dancing. So if you can imagine dancing professionally for a few weeks, eating nothing during this period, and then deciding, well, I think I'll have a bite to eat. So there are people who do it, and the question is, well, where do they get their energy? And I think the simple answer is that they get their energy from light. So maybe I'll stop there because I know you have other other questions to ask, and I don't want to belabor the point.
No, that was a great introduction. That makes a lot of sense. I mean, you have to think back to the fact that we, this story of evolution began with bacteria, archaea, and the main way that these initial organisms really got their energy was from light. It wouldn't make a lot of sense that it would just be completely eliminated and we would just need food. And actually, there's some research coming out that even if we take in chlorophyll, we can actually make energy from that via our mitochondria just by ingesting it and just having the sun hit our skin. So there's definitely a lot of interesting research with the idea that maybe a calorie isn't necessarily a calorie. The way that we look at thermodynamics and calories in the body might require this missing piece, which I think is really water. What exactly is the fourth phase of water? What does it look like, and why is it called structured?
Well, okay. Thanks for asking. Okay. Well, the term structured is actually a kind of misnomer. It means it has structure. Well, everything has structure. You have structure. Your shirt has structure, and the bookcases behind you have structure. And even I have structure. And even the cat that's sitting right next to me and always wants attention also has structure. So the term structure is kind of meaningless. But it does make kind of subtle sense, because by structured, it means organized in some way. I don't know who was the first to use the term structured water, but a guy named Gilbert is a guy who used the word profusely. And in fact, Gilbert Ling was a kind of mentor, hero to me, because Gilbert Ling had been talking about the water that's inside the cell, and he argued for many, many years. He just passed recently, just shy of 100 years old, vigorous until the end. He used the term structured to indicate ordered. And his idea of the ordered water was that each molecule of water was like a dipole, dipole meaning a little bean-like element with minus here and plus here, right? And And most molecules are dipolar, meaning they have more negative charge at one end and more positive charge at another end. And his idea was that these little beams or dipoles could actually line up plus next to minus, like soldiers at attention. And he said, and he argued voluminously, many books, he argued that the water inside the cell was not like water in a cup or a glass, not liquid water, that the molecules were actually stacked or lined up. And that's where I got started, because I had been studying the contraction of muscles at the molecular level, and it occurred to me after many years of working in that field that, you know, in muscles the most abundant component is water. And how come nobody ever talks about water? You know, the muscle is roughly 2/3 water by volume. But if you translate that into the number of water molecules relative to other molecules, it's huge. It's like 99%. In other words, you line up all the molecules and count one by one in the muscle, and 99 out of 100, more than 99 out of 100, would be water molecules, because they're really small. And to make up that 2/3 volume, you got to stuff a lot of molecules in there. So so it occurred to me that how is it possible that the people who are dealing with the molecular mechanism of contraction, how is it possible that they omit the most abundant ingredient in the muscle, and suggesting that it doesn't do anything, it just bathes the more important molecules of life. So that was a kind of turning point for me. And at the time, by coincidence, I happened to meet Gilbert Ling at a conference in Hungary. And I met him, and I also met a dozen or so people who had evidence to support his point of view that the water inside the cell was structured, as he said. And I was overwhelmed, and that's where we got started, because I thought this is so important. And I asked some of my students to read one of his books and feed back to me to get their independent opinion. And the consensus, or I should say the opinion uniformly, was this guy is onto something really important. And if he's right, everybody else is wrong. And so I took it upon myself to write that book, Cells, Gels, and the Engines of Life. It was mainly to illustrate what Gilbert Ling had said in many of his books and talks, but Gilbert's writing, unfortunately, was not so clear. If you're a professional physical chemist with lots of experience and broad knowledge and great intuition, you might be able to get it from his books. But if you're like the rest of us, like myself, maybe you and your colleagues and friends, it's a tough, to really understand all that he's saying is tough. So my goal was to write a book that would be accessible to non-experts. And so I wrote that book, Cells, Gels, and the Engines of Life. And then, of course, having written the book and having an active laboratory, I decided I want to study this stuff. I was so curious about structured water. And what we found eventually, we began calling the fourth phase of water. And it differs from what Gilbert Ling had originally suggested in meaningful ways, but thematically it's very similar. There is order. And so let me tell you what we found about this structured water. We found that it's not stacks of dipoles, as Gilbert Ling had suggested. It's actually sheets. And each sheet is a honeycomb. That is, it consists of repeating hexagonal structures. So, and each sheet forms next to, when water meets certain surfaces, many surfaces, specifically hydrophilic or water-loving surfaces, which includes most surfaces. What happens is that the water molecules transform themselves into this sheet-like structure. So you go from the randomness of ordinary liquid water to a honeycomb sheet. And the first sheet builds on this hydrophilic surface. The second sheet builds on the first sheet, and the third sheet builds on the second, etc. And these sheets keep building, and they can build up to, in some extreme circumstances, up to maybe 1 million sheets of this, what Gilbert would call structured, and we call fourth phase water. We also call it EZ water, EZ standing for exclusion zone. And that came early on from our observation that this kind of fourth phase water excludes particles and solutes profoundly. So as it builds, you see a zone that pushes out all of those solutes, it excludes them. And so we call it exclusion zone. And that term stuck. The reason it's stuck is because exclusion zone, EZ, is easy to remember, you see. So a lot of people pick that up, but it doesn't work in most other countries because instead of Z, they say Z. So it's EZ water instead of EZ water.
Right.
But anyway, so the first property of this fourth phase water is that it's built of stacks of honeycomb sheets. Second one is that it's not neutral. So ordinary liquid water is neutral. This water is typically negatively charged. And the region beyond, when these sheets, beyond the extent of these sheets, is actually positively charged. So the sheet region, the EZ region, the fourth phase region is negative, the region beyond is positive, which gives you a battery. And that's the battery, that's the energy I was referring to, it's the energy that you use in your body as adjuncts to food, to give you energy inside your body. So that's the second. And the third I already mentioned. The third is that it gets built from light. And we found in studies that have been published that the type of light that's most effective for building this is infrared light. So we're all familiar with visible light, with wavelengths running from at the short end, the ultraviolet light, at the long end to infrared light, or to red light, and this is beyond red, this is infrared. And we found that even tiny amounts of infrared light could be extremely effective at building these sheets, building the EZ or fourth phase water. We had an experimental setup where we used a light emitting diode, really weak light emitting diode, emitting infrared light, and we could actually see a 10 times expansion of the fourth phase, of the amount of fourth phase water. So it's very powerful. Now, other wavelengths have some effectiveness, but not nearly as much as infrared. And a lot of people don't know or understand really where you find infrared energy. So let me just address that at the moment because it's really important. Most of us think, oh, infrared, scratching our collective heads. What's infrared? Oh, yeah, my toaster. If I put the bread in the toaster and push down, I can look inside and I can see those glowing coils, and they're hot, and they're generating heat and infrared energy. Okay, so we know that, but in fact, everything is generating infrared energy. If you were to turn off all the lights in your room and whip out an infrared camera, that is a camera like your cell phone camera, except the sensor, instead of detecting visible light, it detects infrared light. Then even in total darkness, you get a beautiful view of everything, including your earbuds and you and your shirt and your bookcases behind you, and even the light switch that you can see. And the reason is that everything is generating infrared light, though not as much as the coils in the toaster, but plenty. Also, inside your body, you're metabolizing all the time, generating heat. And that heat is essentially equivalent to infrared. So you yourself have infrared energy coming from both inside and outside your body. And what that means is wherever you have a water meeting the right kind of hydrophilic surface, the energy that you need to build that fourth phase water is there. It's in the environment. It's all over the place. And therefore, you will always have a certain amount of easy water. And if you add more infrared energy, then you get more easy water. So it's as simple as that. So yeah. So to conclude, your question, yeah, fourth phase water is structured. It consists of sheets, of honeycomb sheets. These sheets build on one another. They contain net negative charge, and they're built by the energy coming from light, particularly infrared light. Okay, I hope that answers your question.
Perfect.
Maybe it's more than you asked for.
Right. So something that, after 2 years of college courses in biology and some research on my own, that's really been nailed into my mind. And what I want to get into right now is this idea of structure and function, how structure is directly tied to the way that something functions. So you're talking about these sheets of water that is their structure. That is how they, that's what happens in response to something like infrared light, for example. So how exactly does that, what relevance does it have for inside of our body? Because I know that blood vessels, for example, correct me if I'm wrong, the outsides are actually, or the inner lining is hydrophilic. So that's possibly where that structured water could come in. So how does that actually affect our health?
Yeah, okay, but let me just a brief correction. I hope I don't forget your main question. It's not just the inside of the membrane, also the outside that are hydrophilic. Is basically every solid that exists inside your cell, and that includes proteins. And the protein surfaces are not completely, but mainly hydrophilic in nature. And the same thing with nucleic acids. And so basically, all the junk that's inside your cell, all the stuff, it all has the kind of surface that nucleates the growth of easy water, fourth phase water. And that's why your cell is actually filled with it. And it should be fully filled with it if your cell is healthy. And that's the basis of your question. How does that relate to function? Sometimes, let me just digress for a moment. If your cell is not filled with enough, then the function could be compromised. And that's why you may need additional buildup of this kind of water to achieve proper function. But your question is more fundamental than that, and it's different from what you learn when you study biology, completely different from the textbooks, because what you learn in biology is that water is not quite irrelevant, but practically irrelevant. It's just a bathing medium for the more important molecules of life. And people who are studying those molecules, basically, they almost completely ignore the water as though it doesn't exist. However, the evidence is that water is in fact absolutely central for everything the cell does for function. And let me explain how, because that is your question. How? And so if the cell is just sitting there doing nothing, like let's just take a muscle cell, for example, because it's a typical cell. It is one that I do know something about, but it doesn't matter. It could be a nerve cell or a secretory cell or a kidney cell, whatever. So the muscle cell is just sitting there. It doesn't do anything, and it's waiting for a signal to contract. Okay, and the water inside that cell, the evidence shows, the water is fourth phase water. Essentially, all of the water is fourth phase water. And that is, by the way, slight digression again, the reason why anybody who sticks an electrode into a cell will report a negative electrical potential. This has been known for 60 years, and there are very complicated mechanisms that have been brought forth, and I've addressed those, and without going into detail, I believe they're erroneous. However, there's a very simple explanation for it, and that is, since the water inside the cell, EZ water, is negatively charged, the cell is negatively charged. So it's simple, and there's a good deal of evidence to support that seemingly radical conjecture. But okay, so the muscle cell is sitting there. It's doing nothing. It gets a signal to contract. Well, the first thing that happens is that the water undergoes a transition between EZ, or fourth phase water, and ordinary water, liquid water that you drink. And this transition is a trigger. The entire cell will undergo this transition. And what this transition does is it enables the proteins to undergo folding. And the folding of proteins is actually what drives the work of the cell. So in the muscle cell, it would be the main proteins in the cell, actin and myosin, that undergo their folding action, and your muscle contracts. Okay, and then after the contraction is finished, the muscle wants to relax, or you want your muscles to relax, and the water and proteins undergo their transition back to the original state, to the relaxed state, and that is, the water then becomes structured, ordered, fourth phase, and the proteins go back to their original relaxed state. The entire process is called a phase transition. It involves the water and the protein. And the same occurs well, I can't say it occurs in every cell because we haven't studied every cell, but we've studied, a fair number of cells, and that transition appears to be a central factor in creating the action of the cell. And so the second part of your question is, well, what does that mean for health? Well, see, since action or function involves a transition from a state where there's lots of fourth phase water to no fourth phase water, and then back again to the original, in order to achieve that action, the original needs to be there. It needs to be, so if you don't have this fourth phase water, the action of the cell doesn't work, because that's what's needed to get everything going. Or perhaps less extreme, if you don't have enough of that water, then your cell maybe can function, but doesn't function quite as well. So reverting again to the muscle. So if your muscles have been exercised perhaps to the extreme, you wind up in the contracted situation. Your muscle contracts into a knot, and it doesn't want to come out of that. You see, and the reason is that you need energy to return to the initial condition where you have the ordered water and the proteins in their relaxed state. So your muscle stays in this contracted state until you can muster the energy to restore function. And so you want to make sure, the bottom line is that your cells really do need a full complement of that EZ water in order to function properly, and so you need to get it. And so you didn't ask the question, but I'm going to address anyway. Well, how do you get it? It's important for the function and therefore the health of the cell, but how do you get all this EZ water? And if you ask me, I can go into and tell you a half dozen really simple ways that you can improve your health through this agent of increasing the amount of hydration, shall we say. It's really hydration. If you don't have enough of this water, you're dehydrated. And so how do you get your cell fully hydrated? So if you ask me, I can tell you, but it takes a bit of...
Yeah, before we get into that, I really want to get kind of dig into the rabbit hole of how exactly does that happen. So I'm a neuroscience student, so I look into, like the central nervous system mainly. And so if I'm going to pick up this pen, for example, how exactly can you take me through how the water would turn into fourth phase water to then contract the muscles? How would that happen mechanistically?
Well, yeah, I mean, so your basically your nervous system sends a message through a nerve and a nerve terminal that ends on the muscle. It says, "Hey, time to contract because I want to pick up that pencil." Um, and so this sort of triggering signal hits the cell um, and initiates this phase transition. Okay, and the phase transition, as I mentioned, phase transition involves uh, the water and the protein together, and then um, so the particular muscles that you need to be innervated in order to pick up the pencil, your brain tells the nerve which nerves to fire, and therefore um, which muscles to contract, and then you're able to pick up your pencil. Is that what you were hunting for, or okay?
Yes.
Yeah. Okay. So yeah, that part makes sense to me. Um, it's not that part's not so complicated because the nervous system is basically the brain is useful for making decisions like that. That I've got the pen in my right hand, not my left hand, so the muscles in my right hand should do the contracting, and the signal from your brain goes through the nervous system to the muscles that control your right hand. And there it is. And when it's all done and over with, and you've picked up the pen and maybe dropped it on the table, your brain says, okay, I don't need to contract anymore. It's time to relax. And the signal says, okay, well, we can relax now, turn off. And then the water and the proteins are then signaled to return to their initial state. And that's where the energy comes in, because in order to return it to the initial state, the body needs energy. So is that okay?
Yeah, no, that was perfect. That was perfect. So without this, this fourth phase water being formed, then there would be no possible way for that protein folding to occur.
Um, well, I hesitate to say that there would be no way, because there can be other triggers. I'm trying to think of what those triggers might be. I mean, this is the natural course of triggering, but for example, a mechanical stimulus like you press on, and there might be a local response to that mechanical signal. That could be also, but this is the reason I hesitate is that we've studied many muscles, and you can take the muscles out of the body and put them into a chamber, into a bath of some sort, and there are many ways that you can stimulate the muscle to contract, but they're not the natural ways that occur inside the body. And that's the reason I hesitated, is that those are possible signals that can do it, but outside the body. Whether they might somehow work inside the body remains open to conjecture.
So today I want to interrupt this show by talking to you about a company which I love and have personally been a customer of for a few years now. This company is Hugh Kitchen. Now, after battling some autoimmune diseases and being totally turned off by the cardboard tasting health foods most companies offered, the founders of Hugh Kitchen not only committed themselves to using the cleanest, least processed organic ingredients, but they also did not compromise on the taste. Now, as a regular customer and having personally tried pretty much everything they have to offer, I highly recommend it, especially if you have trouble with gluten or want to try going paleo and lower your sugar for a little while without having to compromise. Now, from fully organic, grain-free, delicious crackers with a hint of rosemary to dark chocolate, lightly sweetened with organic coconut sugar and filled with almond butter, my mouth is watering. There is zero need to live a bland lifestyle while still staying on track with your health goals. Now, this might be a little late as the holiday season is wrapping up, but they're also great to give as health-conscious gift for friends or family. Since you're hopefully a loyal podcast listener, you can get 15% off your entire purchase using code Jorge15. That's JORGE15. The link is in the description. Back to the show. Okay. And then we talked a little bit about this a few minutes ago, but you said that structured water could bring some energy to cells and does bring energy to cells. And now I know that the mitochondria is obviously incredibly important in creating energy in the form of ATP. So what is the link between easy water and mitochondrial function?
Well, there might be a direct link. First of all, let me address the ATP issue. So it's not one of those things that everybody knows that the energy comes from ATP. However, what few people know is that it might not be correct. And this is not coming from me. This is actually coming from the studies of Gilbert Ling. And Gilbert Ling, I don't know if his website is still working. It was gilbertling.org. And in it, he quotes some studies from way back when, 70, 80 years ago, when the concept of ATP arose. And it was a real breakthrough. People thought, finally, we figured out where the energy comes from. And the energy supposedly lies in a high energy phosphate bond in ATP. And that story has been perpetuated over the years, and it still is the most common story, and it may well be correct. However, it was challenged. It was challenged 1 or 2 years after that critical, famous paper was published that described the high energy bond, phosphate bond. And the people who challenged it said, hey, you guys, you had it wrong. You made a miscalculation. There's no high energy bond at all. Your arithmetic is wrong. And that challenge has never been addressed by anybody. And Gilbert Ling has quoted it. It's quoted in his books, if anybody is particularly interested. And it may be, if his website is still live, it's probably there on the website as well. So I bring this up not to say that the concept is wrong, but to say that some competent people thought for sure that it was wrong and it needs to be addressed. Okay. So your question was not specifically about ATP, and remember, I'm not sure if it's right or wrong, but only to bring up the point that it needs to be addressed. That's all. The function that Gilbert Ling suggested for ATP is, he called it a cardinal adsorbent. That is, it's a molecule that sticks to the proteins or sticks to other places and facilitates the buildup of structured water. That was his idea. And I think there may be some merit or truth to what he's talking about. I don't challenge that. So that, now what about the mitochondria? Okay, so if you look at the structure of the mitochondria, it's pretty interesting because it looks like it's just filled with membranes. And these membranes, as you pointed out, hydrophilic surfaces, are just right for building easy water. And so it's possible that what goes on inside the mitochondria is the buildup of easy water. And remember, I said the easy water is negatively charged. And if you stick an electrode in the mitochondria, you find huge negative charge. So it's possible that what the mitochondria does builds negative charge, builds easy water. And that negative charge, we found through experiments, if that negative charge leaks into the cell proper, it'll build easy water. And we found that experimentally. We just have a chamber with water and 2 electrodes stuck in the chamber. And around this negative electrode, it supplies negative charge, negative electrons, easy water builds, you see. So inside the cell, if the mitochondria, and this is conjecture, but this is hypothesis, maybe even speculation. If that charge from inside the mitochondria, that negative charge, that high negative charge, leaks into the cell will increase the amount of easy water, which in turn will perpetuate function or promote function. So this is a possible role of the mitochondria. It's expressed in a different way, but it provides energy for the cell, but in a way that may be different from the way that the textbook would have it. Is that okay?
Yeah, what you're saying, I want to summarize because it's pretty fascinating, is that it's a hypothesis still, but what if the main energy source is actually water, which is, as you pointed out, the majority of our cells, something that's been really dismissed for so long. And maybe ATP is, because I didn't know the fact that ATP may actually facilitate the formation of easy water. Maybe that's just like simply like a proxy or something that facilitates energy rather than being that main energy source.
Well, yeah, and we know from our experiments that negatively charged ions like sulfate, phosphate, and such build easy water. Surfaces that contain a lot of those of the negatively charged ions are usually responsible for building lots of easy water. So it makes sense from the experiments that we've done outside the body to explain what happens inside the body. Yeah.
Right. Okay. So we talked a
and
little
also,
bit.
just a correction. We don't know, you use the term the main source of energy. We don't know if this is the main source of energy. It might be, but it might not be. This needs to be studied. It could be a very substantial source of energy. We simply don't have enough evidence at the moment to suggest how much or what fraction of the energy comes from this kind of negative charges, battery-like energy from easy water.
Right. So it could be just one of the sources.
It could be one of the sources, or it could be a main source. We just don't know.
Right. Of course. So I think we've talked a little bit about, and at the end, I really want to cover what things really build easy water and how we can promote that in our cells. But are there chemicals or are there toxins which actually interfere with our body's ability to form easy water?
Yes. Yeah. So the main one that we studied is glyphosate. Do you know about glyphosate?
Oh, yeah.
Yeah, okay, you know well about glyphosate. Yeah, so for those who don't know about it, it's the active ingredient in Roundup. And, Roundup is a weed killer. It's a poison. And in theory, it's a poison for the weeds, but not for us, you see. So in theory, we can tolerate, that's what we're told, but the weeds can't. And so this stuff is sprayed on plants, and they're genetically modified plants. So the plant, like corn, for example, the genetically modified version is designed to be insensitive to that poison. But all the weeds that are growing that are preventing the corn plant from flourishing they're sensitive to it. So you spray it, and all the weeds die, but the corn, being insensitive to it, it grows just fine, and then we eat it. And so we're eating glyphosate, and the question is, of course, what's the effect on us? Is this one of the reasons why we're becoming progressively more sick, or not? And so, the argument is put forth, and many people argue that this is a serious issue for us. So we decided to study it, and we decided that, since easy water is critical for health, is it possible that one of the reasons why this weed killer kills weeds is because it diminishes the amount of easy water, and then impairs function in all of the cells of these plants that we refer to as weeds. Weeds because we don't want them to grow. And we found that exactly that was the case, and we published the study. And what the study found is that not only did the glyphosate, even at extremely low concentrations, diminish the amount of easy water, really, really low concentrations, but that other agents that have been touted as good for health for thousands of years increase the amount of easy water. See, so the contrast was was powerful, I think.
Right.
So yeah, it's possible. It's possible that many poisons, we don't know because we haven't studied many poisons, but a route um, to the action of these poisons may actually be exactly that, diminution of easy water. You know, and without the easy water, your cells can't function, as I had pointed out, can't function in the way they're designed to function. So inducing dehydration in this way could be, you know, one way of eliminating function, if that's what
That's
someone.
yeah, that's very interesting because I think and by the way, just to clarify for some listeners who may not know, glyphosate is the active ingredient in Roundup, which is really the main pesticide and herbicide that's used worldwide, but in the U.S. Very, very heavily, especially on grains. So the way that I started looking at it, and I actually did a podcast with a Dr. Ailey Cohen. I'm not sure if you're familiar with her, but she has done some work on toxins and done some research on toxins. And really the main way which most people look at glyphosate is disrupting the microbiome. But what you're saying is it could have, you know, even like other detrimental effects and affect us from another angle, which is water.
Yes, that's exactly what I'm saying. Yeah. So be careful what you eat.
Right, right. So are there any other toxins, by the way, that have been studied?
Well, we haven't studied them, and you know, uh, truthfully, one of the reasons we haven't studied them is many of the people doing the experiments are young students working in the laboratory, and I'm always fearful that I want to make sure that people doing these experiments have enough experience and such to avoid exposing themselves to any of these. So I tend to be a little bit careful about doing it. But you know, there are many poisons out there, and a question is, well, the question remains open. Is it possible that some of these poisons work that way? You know, we also studied. This is not a poison exactly, but it impairs function, and that's local anesthetics, or anesthetics in general. So, you know, if you take an anesthetic, uh, your nerves stop working, your muscles can stop working, etc., transiently, of course. And the question is whether it's possible that these local anesthetics impair function through dehydration, essentially um, through diminishing the amount of easy water. We studied 3 different anesthetics, two of them local and one of them general. They all diminish the amount of easy water in dose-dependent ways. So if you consider those a poison, they're not exactly a poison, but they impair function, just like the poison, except the poison is irreversible. This is reversible, and we found the same. So there's good reason, at least to hypothesize that other agents that impair function could conceivably operate through this very simple mechanism.
Gotcha. Now, I haven't personally looked into this, but several, you know, doctors and other researchers that I follow online have mentioned this idea that maybe things like halogens, like you know, chlorine, chloride that's found in pools, or fluoride, bromine, do those things affect our ability to make easy water as well?
Well, we haven't studied those in particular, so I really can't comment. But you know, I associate with a lot of people in the medical field, especially integrative medicine. You know, or alternative medicine, where people are trying to get at the root causes of the body's issues rather than than dealing with reversing some of the symptoms, which is a sort of general feature of allopathic medicine. So the two cultures differ, and 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 those, and I know so many of the people practicing medicine in the alternative group, and many of those people have studied carefully the evidence, and others have even obtained the evidence. And it seems uniform among those people that the agents that you mentioned are not good for our health. I haven't studied the original papers myself. You know, in Seattle, where I live, the day has 24 hours only, and there's just so much you can do. And so I haven't personally examined the literature, and therefore everything I say is secondhand. But I'll just say that among the people who have studied the literature, there's a consensus that these agents are not good for our health. So let me put it at that.
Got it.
Okay.
Got it. Okay, one other question, because I just recently did a podcast on deuterium, or an isotope of hydrogen, and I was wondering, has your lab looked into deuterium and its effect on health?
Well, yeah, I mean, yes and no. We looked at heavy water, and to see if it built into a fourth phase, and it did, though not as strongly as ordinary water. But on the flip side is deuterium depleted water, and that is argued to be good for health. And I'm not sure the reasons why. It might be that because the deuterium, you might say, it impairs the buildup of structured water, because you get less of the structure with deuterium. It might be that is the reason why eliminating it from your body could promote health, because you get more easy water that way. That could be the reason. I'm not sure, but I do know, and I've met and spoken to multiple groups who have demonstrated that if you use deuterium or drink deuterium depleted water, it could promote health.
Okay.
That's the extent to which I'm aware.
Got it. So yeah, I think the main way that I've researched that deuterium has some effect is through this kinetic isotope effect, which basically means that you're kind of slowing down some of the chemical reaction in the body, because it is heavier, and so. But from your research, there has been little impact on easy water. Sorry,
from our research, there has been little impact. What do you mean?
On the formation of easy
well,
water?
Yeah. So, if you use D2O instead of H2O, we found that you can get exclusion zones, but they're not as large as with H2O. The more deuterium you have, the less the buildup of structured, or we say easy, fourth phase water. And so I'm just conjecturing. We don't have evidence on this, that if that's the case, then you're creating dehydration. The more deuterium that you imbibe, the more dehydrated you're going to be. So if you can use water that is free of deuterium, then you might be in better shape. We haven't studied it in any more detail than that, but it's just a conjecture based on what we do know.
That makes a lot of sense. So as we're nearing the end here, I know your lab has looked into not only how light and infrared builds easy water, but certain other compounds such as green juices, turmeric, coconut water. So what can people actually do to enhance their body's ability to create and maintain this water?
Well, exactly what you say. Put turmeric, eat turmeric. when in your food. Coconut oil also is great. Ghee, from clarified butter, we found also. In fact, this dates back to Ayurvedic times, and those people were wise. They knew about promoting health, and still to this day, a lot of people use ghee. And we did experiments, and we published a paper a couple of years ago showing that ghee is supremely able to build easy water, more than almost anything we studied. So, yeah, I mean, that's a recommendation. So sprinkle turmeric in the food that you eat. Coconut water is great. Ghee is terrific. Basil is another one of those. So all of those we found experimentally, all of those at the concentrations that would be reasonable for inside your body, all of those build easy water. So, for the long term, keeping yourself healthy, those would be good ways to do it, and also exposing yourself to infrared energy to build easy water. That's another way. And you can do that by getting in the sun. That's a natural way of doing that. More than 50% of the sun's energy is infrared energy, or a sauna. We don't do that as much in this country as, for example, in Finland or Russia, but that exposes you to heat or infrared energy, huge amounts of energy. And that should be good for health. And that maybe explains why when you come out of the sauna, usually you feel better than when you went in. So those are a few ways. Just one more way is drinking a lot of water, because your body converts that into easy water, or juicing, because what do you do when you juice? Well, you take the water from inside plant cells, and these plant cells are, freshly grown plants, and they should have, and we know they do, easy water inside of them. So you're squeezing easy water from inside the plants and putting it into your own body. Mm-hmm. So that's one other way of getting easy water, and that's why, according to health practitioners, many of them report to me that patient comes in, and first thing they tell the patient, no matter what their problem is, do juicing and drink that freshly juiced water or freshly juiced juice. And inevitably, they come back months later and they're feeling better, irrespective of what their issue is. So, and finally, connecting yourself to the earth. Why should that work? But it does work. For example, you walk barefoot on the beach, you're electrically connected to the earth, or you immerse yourself in a mud bath. And all of these feel good, and you feel good when you do it. And there are lots of proposed explanations for why. And I have my own, and I think it's related to easy water. And why is it related to easy water? Well, it turns out that the earth is not neutral. And a lot of people are not aware, because we don't learn this as students, although my Russian friend who first alerted me to this told me that every middle school student in Russia knows it. And if you look back 50, 60 years ago into the research, there's no question about this. The earth is negatively charged. It's not neutral, you see. It's just that we don't learn about it. And so if you connect yourself electrically to this negative charge of the earth, what happens is that negativity has the ability to run into your body, into your cells. And any regions that are deficient in negatively charged easy water, the negative charge will rush in and build easy water, and you'll feel better. So this is, so all of these explanations, if you will, or suggestions for maintaining good health, they all revolve around building up easy water in your body, because I think that easy water maintaining is absolutely central for every function inside your body.
Now, I know that this is a huge topic and super controversial still, but I want to get your thoughts because you mentioned ghee, and I know that certain other fats are also, can help to build up that easy water. So this idea of saturated fat being kind of the villain in a lot of the dietary guidelines up until very recently, it's still been kind of vilified. So if saturated fat, like from ghee, for example, can be so helpful in creating that easy water, which is, healthful, then, are some of these ideas that it could be potentially harmful? How does that fit in?
Well, I've not studied enough to answer your question, but there is something that I will say. Fat has been uh, labeled as the villain, and we've been advised to stay away from certain fats, but there have been arguments to the opposite, and the central body that has argued the opposite is a foundation called the Weston Price Foundation, and that foundation is based on the work of Weston Price, and Weston Price was in fact trained as a dentist, but he was curious about why certain cultures maintain good health and longevity and others not. And this was, I think, 100 years ago, close to it. And what he found that the critical ingredient for this, of the cultures where people lived very long and long, healthy lives, is they ate a lot of fat, you see. And this obviously goes against the so-called prevailing wisdom. And the people who are running the Weston Price Foundation have, been espousing high-fat diets for some time, and I think they have a point. And I remember the director, who I met some years ago, emailing me just before Thanksgiving and telling me, be sure to put a lot of butter on your Thanksgiving table. And so anybody who has a question or an issue on this should look at the website of the Weston, Weston Price Foundation, and there you'll find a lot of information on this and a lot of wisdom that underlies this information. So I myself have no experience beyond what I've just told you, so I don't want to come up with any speculation on it.
Right,
but
right.
I will refer you to this foundation.
To me, it makes, it doesn't make a lot of sense that if one food, for example, like ghee, like we just talked about, could be helpful for health in one way, it doesn't really make too much sense for me that it would be harmful in another way. I like to think of like a lot of the healthful habits that we do as being pretty synergistic. If they're helpful for one thing, or if they're negative for one thing, they're like glyphosate, for example, they're probably negative for a lot of different aspects of our health. So, yeah.
Yes, I agree. And also, this just reminds me, I know we're running out of time. It's a philosophical point that nature, I'm convinced, works in a simple way. And if it looks complicated, if the mechanism that you're looking into or studying, if the textbook version is very complicated and it challenges your gray cells to figure out how it really works, it's probably not a difficulty that lies in your brain cells for trying to understand it, but it may be that the mechanism itself is erroneous. You see, simplicity is really important, and science has moved in a way such as to champion complexity instead of simplicity. many of my colleagues, my academic colleagues, would get up there and present a story about some mechanism in biology. And the implicit message is, hey, guys, look how complicated that is. And this subtle secondary message is, well, look how smart I am for being able to figure out how this complicated system really works. And meanwhile, the listener is bewildered, and the presenter looks highly intelligent because they can figure out all these complicated things. Well, I don't buy it. I think nature is really simple, and that if you're onto a mechanism, and that is reverting back to the fat business, it should be simple. It shouldn't be that an agent works by many different mechanisms, like ghee, for example, could be positive in one sense, negative in another sense. Because of many possible receptors to ghee or actions of ghee, it's possible, but it's hard to swallow. A simpler argument is that ghee operates in one major way, and if you can figure out that, you'll understand how it operates in your body. So this is a philosophical point, and I feel justified, having done science for more than a half century. I guess I have license to philosophize a little bit. And the bottom line, for me anyway, I might be totally wrong, but I believe in simplicity of nature, in so-called Occam's razor. If you have two mechanisms, one is simple, one is complicated, the simple one is likely to be the correct one.
Right, and I think what you're saying is phenomenal, and it's absolutely true from the research that I've been doing in the past few years. I wrote a short ebook called Return to Human, and in it I talk a little bit about some of the flaws with allopathic medicine and some of the really kind of narrow-minded and research within the biomedical sciences. And it's exactly what you're talking about. It's zooming in on one tiny little mechanism and trying to sound as smart as you possibly can. And then once you zoom out of that research, you start to think, how is this applicable in any way? Whereas, if you look at a loose ancestral narrative and you think, okay, how did we used to live a few million years ago? We rose and set with the sun. We ate foods that were, right there. We picked them right off where they were at their highest nutritional value. We did all of these simple things. And like you said, we were grounded. We're barefoot walking on the ground, all these simple things that we've, kind of come to be disconnected from in the past few years. I think simplicity, absolutely fundamental.
I'm glad we agree. I think for me, this is, really important. Even Einstein was there for simplicity, although I must admit, and he did say, nature works as simply as possible, but sometimes you have to add a little bit of complexity to make it work. And I think he said that. He said it in a more brilliant way than I'm reiterating, but he was referring to relativity, which is not so simple to understand. But anyway, we leave it at that. I'm glad we agree. I think this is a really important principle, the principle of simplicity, which has dominated science since the time of Newton. How many hundreds of years ago? And during the past 100 years or so, it's changed. It's changed with physics, mostly with the principles of quantum mechanics and quantum electrodynamics, which are based on, on abstract mathematics rather than intuition. I think it's necessary for us to return more to intuition in dealing with science, intuition and simplicity. So maybe that's a good way to end with a little bit of philosophy.
Yeah, to finish up here, I like to ask a few final rapid fire questions,
Sure.
Which I ask all my guests. So number one, what is the most important health promoting habit that you personally do every day to support your health?
Oh my goodness. Well, I can tell you, I've had a couple of health problems, and the naturopath who I'm seeing is interested in overall health and wants to keep me going strong for at least 40 more years. And she said the two most important things, and are exercise and eating lots of vegetables. So I've changed my life pattern to doing those two, and I do them. I actually would follow so much of the kinds of things that we've been talking about, but time is a real issue for me, and I struggle with that. And where I live in Seattle, the day has only 24 hours. I'm not sure where you live in Michigan, maybe it's longer, but I try to fit everything into that time, and it's a real struggle for me to do that. My late wife used to tell me that I'm running 5 careers simultaneously, and I think she was right. So I can't do all the things that I think are important to do, and it's a kind of balance between them, because some of them take time, and I'm simply out of time. So is that an adequate answer to your question?
Absolutely. Number 2, what is the most important or the coolest thing that you've learned recently?
Oh my goodness. Okay. Okay. Sailboats. So I'm writing a book. My next book is about the role of electrical charge in nature. And I think it's all over the place, grossly underestimated. I think that electrical charge is responsible for so many things in our life that we don't recognize, ranging from what we were talking about in the cell, but way beyond to questions like what turns the earth, so we spin every 24 hours, what makes wind, what makes weather, what's responsible for gravitation, how do birds fly, how do fish swim, et cetera, et cetera. And I learned recently, actually I kind of knew about it, but I learned more recently about sailing. I'm not sure if you sail, but sailing is something really unusual. Sailing downwind is no problem, because you can imagine the wind is blowing on the sails and pushing the sail. The pressure of the wind on the sail pushes the boat downwind. That's a no-brainer. But sailboats can go upwind also, and that is a shock. Now, when I learned to sail as a young faculty member, I couldn't figure it out. I read the book and it didn't make sense. So the sailboat couldn't go directly into the wind. It could go at some angle to the wind. And, I was told, well, read the book and you'll find out why. And I read the book and I couldn't understand why. It seemed very complicated. And a colleague of mine physicist, wrote a book a few years ago on sailing. And in order to explain sailing upwind, or at least partially upwind, required 3 chapters. It's very complicated. And, as we discussed, it's complicated. You scratch your head, something wrong. And so the thing I learned fairly recently, which makes the whole thing so simple, is that there are some kinds of sailboats that can go almost directly into the wind. And when they go directly into the wind, you don't need vector diagrams to underlie complicated explanations. It's very simple. The wind is blowing this way, but you're going against the wind. So it's like if I'm pushing you, instead of pushing you back, instead of moving backwards toward the door behind you, you move toward me. I'm pushing you and you're moving toward me. Unbelievable.
Right.
But, right? Unbelievable. Yet, there are 2 classes of sailboats that can do that. One of them is a sailboat that runs on ice. It looks like a regular sailboat, but it runs on runners. So the friction is very small and there's no pushing through the high viscosity water. And they can go almost directly into the wind at speeds of 100 miles an hour. It's
Wow.
like a gale force wind on your face, but you're moving into that wind. Explain it. And this also invented by the Chinese several hundred years ago, many hundreds, a so-called land yacht. It looks like a sailboat, but it runs on wheels. So again, no friction or almost no friction, no plowing through the water, and also it runs almost directly into the wind. You see, so same problem. The people who are sitting in the boat, they feel the wind on their face. So I'm sorry for the length of the response, but why is this so interesting? It's interesting because something is missing from the equation, right? It can't be that I push you and you move toward me instead of away from in the direction I'm pushing. And if that were true and you can explain it just by that wind, Newton would be turning over in his grave. It doesn't make any sense whatsoever, you see.
Right.
And there comes the role of charge. And so without going into detail, I think that the sails become charged as they move through the wind, as anything becomes charged as it moves through the wind. And very simple explanations, which I won't go into because I need a diagram, can explain how the sailboat moves into the wind. And that's coming in the next book. So it wasn't something that I found out yesterday, but it wasn't so long ago either.
Right.
Okay.
And we'll find that out in your next book.
Yep, sure. Okay,
Awesome.
hopefully within the year.
Awesome. So where can people find out more about you and your work?
My lab website would be one way. That's probably the best way. There are many talks online, but the website is the best. And if you ask me for the URL, I can't tell you, but I can give it to you afterward. Or if you look under my name, Gerald Pollack Laboratory or something like that, University of Washington, you'll find it right away.
Perfect. I'll have the links to all those in the show notes so people can
Sure.
find you.
Yeah, in the book, I would recommend, look on Amazon under the fourth phase of water. It's become really popular, and there's a lot in it.
Great.
Yeah.
Thank you very much for your time.
Well, thank you. Your questions were great. Thank you, Jorge. Okay.